Hello. We have defined till now crystal as periodic arrangement of atoms and lattice as periodic set of points. In this video, we will look at the classification of lattices. Lattices are periodic set of points and the periodicity can vary in the three directions of a space. So, the axis and the angles of the crystal can have many different values. So, it is important to have a system of classification of these lattices. Two important systems are in common, 7 crystal systems, one of them classifies the crystal into crystal systems, 7 crystal systems and the another one into 14 Breve lattices. So, let us look at them. Here is the list of 7 crystal systems. We have cubic, tetragonal, orthorhombic, hexagonal, trigonal or rhombohedral. So, there are two alternative names for the same system, monoclinic and triclinic. Each of these systems have a conventional unit cell which we have shown here. So, in the cubic system you have a unit cell in which all sides are equal, A equal B equal C, all angles are equal, alpha equal beta equal gamma and all these equal angles are equal to 90 degree. So, basically you have a cube as your unit cell and that unit cell is repeated in space to generate the entire lattice. Tetragonal lattice, tetragonal system has a unit cell, conventional unit cell which is almost like cube, all angles are equal to 90 degree, two sides are equal, but third side is not equal. Orthorhombic, also all axes are mutually orthogonal, all angles are 90 degree, but none of the three sides are equal. Similar relationships are given here for all other systems. You do not really have to worry about memorizing all this in one go, but gradually you will become familiar and in case if you need sometimes and you do not remember, you can always look it up in some book. But let us try to understand the meaning of the crystal system and Breve lattices. So, 7 crystal systems, we have 14 Breve lattices. In each crystal system, there are one or more Breve lattices. P, which stands for primitive or simple, is present in all of them. So, we have 7 primitive or simple lattices, one each in the 7 systems. So, P stands for primitive or simple and which means lattice points are only at the corners of the unit cell. The next type is I or body centered. Body centered, which means lattice points are at corners as well as the body center. This Breve lattice is present in cubic, tetragonal and orthorhombic. So, we now have 7 plus 3 10, 4 more Breve lattices are there. F stands for face centered, which means lattice points are at corners. Corners will always have lattice points, whether in simple or body centered or face centered. Corners plus all face centers. F is there, you have cubic F and you have orthorhombic F. So, 2 F lattices are there. Finally, C is called either end centered or it has an alternative name also, base centered, end centered or base centered. Here the lattice points are at corners and not on all faces as in face centered, but only on one pair of parallel faces. The C centered or end centered lattices are there in orthorhombic and in monoclinic. So, we have now 7, 7 P, 3 I's 10, 2 F 12 and 2 C 14. So, this constitutes the 14 Breve lattices. Let us familiarize ourselves little bit more with these Breve lattices. So, let us look at the 3 cubic Breve lattices. In the cubic system we said we have P, we have I and we have F. So, what do they look like? So, this is my cubic unit cell and when I say cubic P, or primitive cubic, or simple cubic, more common name is simple cubic. So, the Breve lattice name includes the crystal system name as well as either the symbol cubic P or in language we can say simple cubic. And the simple cubic lattice will have, the simple means the lattice points are only at the corners. So, only corners are identified as lattice points. Do not think of these as atoms, they are only points. I am highlighting them to emphasize that the lattice points are only at the corners. Let us draw the next one. Let us draw cubic I. This will be body centered cubic. Both names are synonymous or equivalent. So, you can say cubic I or you can say body centered cubic. Here the lattice points will be at the corners. As I said, corners will always be lattice points, but there will be an additional lattice point right in the center of the cube. So, this will be the body centered cubic lattice. And finally, let us try to draw the face centered one. that is the cube. As usual, lattice points at the corner. But to qualify it as cubic F or face centered cubic, we have to give additional lattice point at the centers of all the faces. So, at the center of left and right face, at the center of bottom and top face, as well as at the center of the front and the back faces. So, all 6 faces will be centered. So, then we will have a cubic F lattice. So, that is the meaning of these symbols and the location of the lattice points. Cubic system does not have end centered, or as we said, can be called base centered also, but orthorhombic has. So, let us look at the example of base centered in an orthorhombic. Orthorhombic has all 3 sides unequal, but axes are still at 90 degree. So, that is my unit cell box, and the location of lattice points at corners, and to make it base centered or end centered, I have to center one pair of opposite faces, one pair of parallel faces, not all faces. If I center all faces, I get the face centered lattice, but if I center, let us say, only the bottom and the top faces, lattice points, additional lattice points only on one pair of faces, then I end up with end centered or base centered orthorhombic lattice. It is called orthorhombic C because if I choose my axis, if I choose my axes x, y and z in this way, note that in crystallography the A is along the x axis, B is along the y axis and C is along the z axis. So, the face which we have centered is the face containing A and B. This face is called the C face, capital C face. So, when I say orthorhombic C, I mean orthorhombic C, this means C face is centered. Of course, one can have, if I had chosen to center the other faces, I can have orthorhombic A, orthorhombic A or B also possible. However, since only one pair of face is centered, you can always choose your z axis or the C axis perpendicular to that face and make it orthorhombic C. So, we have seen we have simple where only corners are there, corners as lattice point. Then we had face centered F, then we have body centered, and we also had a base centered or end centered. So, the question can be asked, why do not we have any lattice which we can call edge centered? By edge centered, we will mean points at the centers of each edge. So, let us consider edge centered cube. So, points at corners and at centers of each edge. Centers of each edge. Let me construct one unit cell like that. So, again I have my cube, I put points at the corners and I also put additional point at the centers of each edges. The centers of each edge. Why is no lattice? Why is listed like this, an edge centered cubic lattice or an edge centered orthorhombic lattice? The answer to that can be seen by examining the surroundings of the point. So, let us look at point A. Let me call this point A and let me call this point B. And let me choose this direction as my x direction. So, if I move from A and let me call the edge length of the cube as A. So, if I move from point A in the direction x at a distance a by 2, I find another neighbor, this one. But if I move from point B in the same direction, that is in the x direction, the same distance a by 2, I do not find any additional point. So, we conclude that points A and B are not equivalent. Points are not equivalent, not translationally equivalent. So, the set of points do not form a lattice. So, let us again look at the complete list of Breve lattices which we had. So, we were having cubic P, simple cubic, cubic I and cubic F. We had tetragonal P and tetragonal I. We had orthorhombic P, orthorhombic I, orthorhombic F and orthorhombic C. So, orthorhombic is quite rich, it has all the 4 varieties. We have hexagonal P, and that is all. We have trigonal P, we have monoclinic P and monoclinic C, and we have triclinic P. So, we can see that 7 different lattices, 7 different crystal systems are there, and in each crystal system, like in orthorhombic, 4 possible Breve lattices could have been there, P, I, F and C, but only orthorhombic has all 4. So, 7 systems, 4 types, 7 into 4, 28 lattices were possible. Possible lattices, but we have only 14. But only 14 Breve lattices. So, why so many other lattices which were possible, but are not there? In particular, why do not we have cubic C? Why cubic C is absent from the Breve list? Of course, similar question can be asked for all other empty boxes. Why is tetragonal F not there? Why is tetragonal C not there? And so on. So, all these empty boxes is a question mark, and it is this question which we will take up in the next video. So, this will be our starting point for our next videos.